So we've been talking about hydronium ion concentration at pH and what that means. Now we're going to look at acid solutions. There are two possible sources of hydronium ions in a solution that contains an acid. The most obvious one is the ionization of the acid itself, right? But we also have the auto-ionization of water. Any aqueous solution is going to have some hydronium ion in it. Most of the time, we can ignore the auto-ionization of water because that's going to contribute a very, very small amount, roughly 10 to the minus 7 of hydronium ions, and so it doesn't really matter. But if we have very dilute acid solutions, like less than 10 to the minus 5th molar, then we have to consider that. So strong acids, by definition, ionize completely. And so the concentration of hydronium ion in a strong acid solution is equal to the concentration of the strong acid. So this is very straightforward. If we have 0.10 molar HCl, then the hydronium ion concentration will be 0.10 molar because there's one ionizable hydrogen for every molecule of HCl. And if you put that into the pH equation, you get a pH of 1. Weak acids are a little trickier. They require solving an equilibrium problem because weak acids only ionize partially. So here we're making an ice table and just saying that the initial concentration of the weak acid is 0.1. Here, the initial concentration of the hydronium ion is approximately 0. It's actually 10 to the minus 7, but that's negligibly small compared to 0.1, so we say basically 0. This is 0. And then the change, of course, some of this will ionize, so this is negative x plus x plus x, and we come up with these equilibrium relationships. And so if we look at the equilibrium constant for this ionization, it's going to look like this. And that's going to be x squared over 0.10 minus x. So there's an equilibrium constant for that, and it has a special name. That's called Ka. It's the acid ionization constant. So find the hydronium ion concentration of a 0.25 molar hydrofluoric acid solution. Well, I mean, the problem is titled Finding of a Weak Acid Solution. But hydrofluoric, is that a weak acid or a strong acid?
It's strong. Or weak.
It's a weak acid. Why?
Fluorine is extremely electronegative and does not go pH.
Well, there's that, and then there's also because it's not on the list. Right?
Wow.
Sorry. No, but your explanation was really good. It was really good. But there's 6 of them. And so if the acid you're dealing with is not one of the 6 strong acids, it's a weak acid. So here we have, we're given the Ka value and an initial concentration, and we're asked to find the hydronium ion concentration. So we need to set up an ice table. So I like to put the reactants and products in here kind of identify what I'm doing here in my ice table. So initial concentration of the hydrofluoric acid is the stated concentration, 0.250. For hydrogen ion or hydronium ion, it's approximately 0, and for the fluorine, it's 0. So some of the HF is going to ionize, so we're going to lose X of that, and we're going to gain X of this and X of that. So we end up with 0.250 minus x, x, and x. So we can say that, well, let's do it that way. Ka is equal to the hydrogen ion concentration times the fluoride concentration divided by the hydrogen fluoride or hydrofluoric acid concentration. So we've got 3.5 times 10 to the minus 4. And when we take our equilibrium relationships here, we get x times x, x squared, divided by 0.250 minus x. It's a little messy. And how do we find what x is? You plug it into your solver. Could we use x is small here? Maybe. 0.008. 0.009. Yeah, so then that's not small, is it? So he's got it in his solver already, but I need to do it myself because just that's how I am. I think scientists tend to be like that. It's like, well, yeah, that's great that you did that. Now I need to prove it to myself. Yes, you were very right. So x comes up as 0.00918. So then the hydronium ion concentration, well, the hydronium ion concentration is x here. Yeah, question?
Never mind. It just makes sense.
Okay, good. I love those questions that answer themselves. So the hydrogen ion concentration, which is the same as the hydronium ion concentration, just two different ways of writing the same thing. 0.00, 2 sig figs. Molar. Now, we can just check on whether we could have used the x is small approximation, and to do that we're going to compare what x is to something that we subtracted it from. So we take x divided by 0.25 times 100. Oh, actually we get 3.7%. So yeah, it's kind of on the borderline, but we could do it that way. Let's do it that way, just because we can. So, using x is small, we've got 3.6 times 10 to the minus 4 is equal to x squared over 0.250 minus x. And in the x is small approximation, we're saying that x is small enough that when we subtract it from 0.25, it doesn't make any difference. So we just leave that out. So x ends up being the square root of 0.250 times 3.6 times 10 to the minus 4. .00949. So, because the Ka has two significant figures, it's probably most correct to say that this has two significant figures, and then that difference between .0092 and .0095 is not concerning. Any questions? Find the pH of a 0.0150 acetic acid solution. Ka is 1.8 times 10 to the minus 5. The problems in the textbook do not give you the Ka value in the problem. They make you go back to the table and look it up. But it gets super tedious doing that in the PowerPoint, so I just type them in. So, acetic acid solution. Now, I know what the formula for acetic acid solution is, but what if it's something I don't recognize? I can still do the problem. I could just use HA as a generic acid. So I'm just going to do that because this acetate's kind of a pain. It's got too many letters and numbers. C2H3O2. So we've got H plus and A minus. Initial change, equilibrium. Initial concentration, 0.0150. What are the concentrations of the other two things? 0. Yep, question?
What if it's a diprotic acid?
That's a good question. What if it's a diprotic acid?
Maybe 2H plus?
Oh, yeah.
Well, the thing is, if it's a strong acid, there's only one strong acid that's diprotic, and it's only strong in its first proton. If we're looking at a diprotic weak acid or a triprotic weak acid, we have to look at each of those coming off separately, and we'll get to that in a minute. Thanks for bringing it up. So then we write in our changes. Ka 1.8 times 10 to the minus 5. It's going to be equal to x squared times nothing divided by 0.0150 minus x. Honestly, with a TI-36X Pro, I think it's just as fast to plug it in rather than try to do it with x's small.
I think X is.
Well, it probably is. Whoops. What did I do over there? Because the book does a lot of x's small problems.
Yeah, it's 3%.
3%. So that's X. X is the hydrogen ion concentration. So the pH is negative log of that. What I'm going to do on my calculator is I'm just going to use the value that was given by the solver. Wait a minute. Sorry, I'm lost in my calculator. Never mind, I'm just going to use 0.00051. Oh, it was giving me the answer and I didn't even recognize it. Now it's just, where is it coming up with this 3.29 business? It's the answer, stupid. 3.29 is pH. Any questions? 3.28. Finding the pH of a weak acid solution when X is small doesn't work. Well, we've got this because we solved it that way the other two times, right? So here we have a nitrous acid solution. They gave us the formula this time, so I'm going to go ahead and use it. HNO2 would be in equilibrium with H plus and nitrite ion. Initial 0.010, approximately 0 and 0. So Ka 4.6 times 10 to the minus 4. It's going to equal x squared divided by 0.010 minus x. Your x is 0.0024. Which is 24% of the number it's being subtracted from. So x definitely is not small. What's our pH? I'm getting 2.62.
Why used every number?
Well, that's better.
It's like 16 digits. But
Yeah.
little skinny fingers here. But that's like a whole tenth. Or tenths. Tenth? Yeah, it's a whole tenth.
24068.
Isn't X 0.001927? Why'd you have that 0.0024?
4.6 times 10 minus 4.
Where are your units? My calculus teacher is rubbing off on me.
Well, if it was a 0.015 molar solution, that's what it would be.
Oh.
Oh, didn't I tell you that's what we were doing? Yeah. I was kind of cheating.
Wow.
I used the equation from the last problem and I just typed in, and I didn't scroll over far enough to see there was a 5 in there.
Oh.
Yeah. Okay. So, Spencer alerted me to a cool feature I wasn't aware of with this calculator. So you do the problem solver and you get an X value, and then you need to go do a calculation, and you're like, but it disappeared. If you type that variable X button, it'll show an X and it'll use that last value. So, very cool. 2.72, that's better.
Oh, so you press X and then enter.
Yeah,
Well, it saves it as X.
saves it as X.
Oh.
Any questions?
That looks like cool.
Well, I guess I should fix this too.
Yeah, that threw me off.
Yeah, sorry about that. That's better. 2.72. Phew. Finding the equilibrium constant from pH. So at 0.175 molar weak acid solution has a pH of 3.25. Find Ka for the acid. So this is different. We're going to approach it the same way, though. We're going to write our equation for the ionization of our acid. And we're going to look at initial change and equilibrium. The molarity of the acid solution is the initial concentration for the acid. And H plus is approximately 0 and A minus is 0. What does the pH tell us?
The concentration of hydrogen.
It gives us the ability to calculate the concentration of hydronium ions. So H plus or H3O plus is going to equal 10 to the negative pH, which is going to be 10 to the negative 3.25. So at equilibrium, the hydrogen ion concentration is 0.000562. So we can fill the changes in using X like we've done before. X amount of the acid is going to ionize, forming X of the hydrogen ion and X of the anion. But now we look at the H plus, we started with 0, it changed by X, and now we've got this final value, so that tells us that X is this value, right? So this other concentration must also be the same. And then here we've got 0.175 minus, this doesn't fit very well, 562. 0.17. That's not what it was. Minus that. 0.1744. So Ka is going to equal 0.000562 squared divided by 0.1744. Anybody else get that? 1.8 times 7 minus 6. Hmm?
I'm just really slow. I had a question about how you got one of those numbers, just because I was writing stuff down.
Okay.
We answered it.
Okay, good.
You look so quick some days.
I like it. Personally.
I feel like I'm going at a snail's pace.
Really?
This class, yeah. 1A is just whoosh,
Yeah.
but this one is like, just, there's so much silence, but
You want us
it's
to talk more?
necessary. No. The periods of silence are you guys actually calculating along with me, right?
There's
You're
not as much math in 1A, is there?
no, and it's not like this.
I'm not asking like I've never taken class before. This was last semester.
You've wiped that from your brain. 1.8 times 7 minus 6. Okay. The initial concentration and Ka of several weak acid solutions are listed. For which solution is the X small approximation least likely to work in finding the pH? So what are we looking for here for X small not to work? small initial concentrations, because then the number that we're subtracting X from is smaller to start with, so that would mean that X has to be even smaller in comparison.
And
Larger equilibrium constant. So we're going to look through here and find the small initial and the large, so it looks like C, right? Yeah. I think there's a problem. So fix the slide. We think the answer is C, and yes, the answer is C. Painful. Which of these solutions is the most acidic? That is, which one will have the lowest pH? Yes, in the middle. A. Would you like to tell us why? Would you like to tell us why?
Yes. So, hydrochloric acid is a strong acid.
Yep.
It's on the list.
It is. It's on the list.
And it has the highest concentration. So,
Well, the HF is higher in concentration for C, but it's a weak acid. Yep.
so highest concentration of dissociated ions.
Yes. Any questions? Because all of the HCl dissociates, and so the hydrogen ion concentration will be 0.1, and for the HF it'll be significantly less. So percent ionization. Percent ionization is the ratio of ionized acid to initial acid concentrations multiplied by 100 to get a percentage. So as with all percentages, it's a part divided by the whole thing. So the part here is how much ionized divided by what there was originally present. The percent ionization is going to be relatively small for weak acids. It will be 100% for strong acids.
What is like the application for this?
I can't think of a direct application.
Because I'm trying to think, when do we use the percent ionization?
Well,
68%.
we'll see something kind of interesting that's unexpected in a couple slides. So find the percent ionization of a 0.25 molar acetic acid solution at 25 degrees C. K is 1.8 times 10 minus 5. Acetic acid comes up a lot.
No, I thought we used the same numbers.
Yeah. Well, we had a 1.8 times 10 to the minus 6.
That was 5.
Well, we used acetic acid before, and this constant is still the same since we did that. So initial concentration 0.250, 0 and 0, change, equilibrium. I mean, when we're doing these tables just for a weak acid by itself, it ends up being like the same every time, right? So Ka 1.8 times 10 to the minus 5 is going to equal x squared over 0.25 minus x. So x is 0.0021. So that's great and everything, but what did we actually need out of that?
Percent.
So we want the percent ionization, which is equal to the amount that's ionized, right? How did they express that back here? H3O. So that's going to be, so we're looking at H plus concentration at equilibrium divided by our acid concentration initially times 100. So 0.0021 divided by 0.250 times 100. .84%. And yes, that is a very small percentage. So when we look at the acid ionization constants and we talk about, the weak acids only ionize partially, I don't think we really recognize how little they ionize, right? And so here, it's less than 1% of the weak acid. Yes?
Won't we do this for weak acids because you said strong acids?
Strong acids will be 100%.
Are you going to put functional as that it's actually strong acid?
Probably not.
Let's just make that one.
Is this same process true for any partially soluble ionic compound?
Except for
Well, I suppose you could. With a soluble ionic compound, you can't really calculate a percent ionization because the initial thing is a solid. And so you can't really identify the concentration. But we do equilibrium calculations with solubility. Yeah, definitely. So, trends for weak acid. The equilibrium H3O plus concentration of a weak acid increases with the initial concentration of weak acid, but the percent ionization of a weak acid decreases as the concentration gets larger. That's not intuitive. So if we have 0.2 molar nitrous acid, we have hydronium ion concentrations that's 0.0096. If we have 2.5 molar, the hydronium ion concentration is higher, it's 0.034, that makes sense. But the percent ionization has actually gone down. It's gone from 4.8% down to 1.4%. And that's like a what? Well, let's look at what happens. So we've got our equilibrium here. And we know that Ka is equal to H plus times A minus over HA. Okay, so that's all very true and everything, but that's not actually what I wanted. Let's think about this in terms of Le Chatelier's principle. Okay, so if I have more HA, that's going to cause me to make more H plus and more A minus. Okay, so the percent ionization is equal to the hydrogen ion concentration over the initial acid concentration times 100. When we did the ICE tables, we ended up with the hydrogen ion concentration being X, so our equilibrium constant would end up with H and A minus both being X, and down here the equilibrium concentration is the initial acid concentration minus X. So this is equal to a constant. If we assume that X is small, then we can say that the initial concentration of the acid is equal to x squared divided by Ka. And then if we plug that into the equation, we've got the hydrogen ion concentration, which is x divided by x squared divided by Ka times 100. And I ran out of room. I'm going to go over here. So percent ionization ends up being Ka over x times 100. Coming from down here, I'm inverting this. So I've got x over x squared, and I've got Ka in the top. So here, what happens then is, as my initial concentration gets higher, my hydrogen ion concentration gets higher, and this fraction here becomes smaller, and so my percent ionization becomes smaller. And that was just not at all very good. I mean, mathematically, it's fine, but it's not at all meaningful. So, my apologies. Yes.
What's the major takeaway?
I'm not sure.
I thought
What's the major takeaway? I mean, these things are true. The hydrogen ion concentration increases when you increase the concentration of a weak acid, but the percent ionization actually decreases. And that's weird. Maybe that's the takeaway. Because the initial concentration is higher, but you don't have the same, it's not just a straight percentage, right?
Right.
Because of the equilibrium constant.
You can assume that it's going to be smaller.
It's going to be smaller, yes, but that's not what we would naturally expect. During the break, I'll see if I can figure out what I actually meant to say. So, which weak acid solution has the greatest percent ionization? C, because the smaller one, right? Okay, mixtures of acids. This is fun. So if we're calculating the pH of a mixture of acids, this could get very complicated. But many times we can ignore the weaker acid and just focus on the stronger one, because the contribution of the weaker acid is not actually significant. So let's look at a mixture of a strong acid and a weak acid. So 0.1 molar HCl and 0.1 molar HCHO2, that's formic acid if you care. So there's three sources of hydronium ions here. With a single acid, there's two, water itself and the acid. Now we have the strong acid, the weak acid, and the autoionization of water. So here we have the strong acid. This ionizes completely, so we have a single arrow. Here we have the partial ionization at the ionization equilibrium of the formic acid, the weak acid, and here we have the autoionization of water. What happens here is we can predict how much hydronium ion concentration is going to come from the strong acid. It's equal to the concentration of the strong acid, right? So then when we set up our ice table here to look at the weak acid, the initial concentration of hydronium is not 0 anymore. It's 0.1 because the strong acid ionized completely. So this is 0.1. Our weak acid is 0.1. And so the presence of the hydronium from the strong acid suppresses the ionization of the weak acid. It's Le Chatelier's principle. You add more product, the equilibrium will shift to the reactants. So we have initially 0 formate, and we have minus x plus x plus x. But now we have 0.1 minus x, 0.1 plus x, and x. And so when we put all this together, so this is for the formic acid, 1.8 times 10 to the minus 4. We're going to get 0.1 plus x times x divided by 0.1 minus x. So that's this guy right here times that divided by this. So if we try the x is small approximation, both of those are gone, and then those cancel out, and x is 1.8 times 10 to the minus 4. There it is faster.
This is
And-
Kay.
Yes.
How does hydronium become a 0.10 again?
Because I have this strong acid. So I have 0.1 molar HCl, and it ionizes completely. So that's where the 0.1 molar initial concentration is coming from. So if I take 1.8 times 10 to the minus 4 and divide by 0.1 times 100, x is only 0.18%, so x is small. So this contribution from the weak acid is negligible. And the contribution from the autoionization of water is far smaller, not even worth calculating. Any questions? What if we have 2 weak acids? Still 3 sources. So we can ignore the weaker acid in the water if the conditions are right. So if the Kas of the weak acid differ by a factor of several hundred or more, if one of them is significantly larger than the other, and the concentrations of the acids are similar, or the concentration of the stronger acid is greater, then we can ignore the weaker acid. We always get to ignore the water. So find the hypochlorite ion concentration of a mixture that's 0.3 molar HF and 0.1 molar HClO. So here we have 2 weak acids. This one has a Ka of 6.9 times 10 to the minus 4. This one has a Ka of 2.9 times 10 to the minus 8. Which one is stronger?
Second one.
Which one has a larger Ka?
Or hypochlorous acid?
The HF. 10 to the minus 4 is bigger than 10 to the minus 8.
Oh, I thought we wanted smaller.
Stronger acid, larger Ka. So this is the stronger acid, and the concentrations are not the same. They're in the same ballpark, but the concentration of the stronger acid is larger. So this is good for making things simpler. So first of all, we'll look at the stronger weak acid. At least we don't have to deal with the weaker strong acid. Initial change equilibrium. So the initial concentration is 0.300. Your initial concentration of H plus is 0, fluoride is 0, minus X plus X plus X. 0.3 minus X, get X and X. So the equilibrium constant here is 6.9 times 10 to the minus 4, and that's going to be X squared divided by 0.3 minus X. X is 0.014. 140 actually. Everybody okay with that? So that tells me that at equilibrium, this weak acid is contributing a hydrogen ion concentration of 0.01 molar. So that's the concentration from this weak acid. Then we're going to look at the weaker of the 2 acids. So hypochlorous acid initial change equilibrium again. The hypochlorous acid is 0.100 molar. What's the hydronium ion concentration? 0.014. And what about the hypochlorite ion? 0. So minus x plus x plus x. 0.100 minus x. 0.014 plus x. And x. So 2.9 times 10 to the minus 8. That's going to equal 0.014 plus x times x divided by 0.10 minus x. I'm going to just try x is small. Be 2.9 times 10 to the minus 8 times 0.1 divided by 0.014. Yeah, x is small. So I can use the x is small approximation and get rid of the plus x and the minus x here. So x is now 0.1 times 2.9 times 10 to the minus 8 divided by 0.014. It's really small. 2.1 times 10 to the minus 7. Yes?
How did you do the 6.9 first? Because that's the stronger.
Yeah, I'm going to do this one first because this is the stronger acid. It's going to contribute more. And then I look at the weaker one. Yes?
Aren't you also doing it first because we're given the stronger acid polarity first?
No.
I may have missed the question. Oh, I didn't even see that.
So, depending on what the question is, like if it was asking for the pH of this solution, would I actually have to calculate this out? No, because adding this or subtracting it from this isn't going to make any difference. The pH is the same. But what are they asking me for? They're asking me for this. I need to find this X over here, the hypochlorite ion concentration. And that's 2.1 times 10 to the minus 7. Any questions? I know. 2.0 times 10 to the minus 7, close enough. Judging relative pH. So of these three solutions, which solution is most acidic? In other words, has the lowest pH? 1 molar HCl, 2 molar HF, or a solution that's 1 molar in, it should be HF.
I was like, what?
Yeah, that's... So, yeah, the answer is A, because,
Oh, me again?
well, I mean, you're the ones,
Somebody else? No?
anybody?
I mean, I just said it like 5 times.
Because it's a strong acid, right? HF with HClO, they're all weak acids. And as we saw with the percent ionization, they really don't ionize very much at all.